Sorry, I have some problems. I'm not sure. Okay, sorry for a while. It doesn't work, so let me put like this. Okay. So even it is not completely in full scale, I think it is fine as well. So
okay, we see it. Yeah.
Yes, let's say we'll talk about the Cherenkov telescope array, and let's say this is quite a nice project. It is a very big one, and currently I am the coordinator of the CTA Transient and Multi-Wavelength Science Working Group in the consortium that is somehow building this array of telescopes. So let's say me discuss first what is the CTA, and then we'll show you how, or a few ideas and how CTA might benefit from a collaboration with Hermes, and in both ways, I think, how we can collaborate together. So CTA is built actually by a consortium of people. We had as here, let's say, a consortium meeting online. In October 2020, we were, let's say, you can read the number, more than 400 people all around the world. And it is nice, so many scientists are actually working on this project all around the world. So CTA is really a big, very big consortium, very large number of people working on this project. So actually the CTA Consortium includes more than 1,500 members from more than 200 institutes in 31 countries, okay? So the CTA Consortium and both the scientists and the engineers of the consortium themselves, let's say, devised the CTA concept, let's say, more than 1 decade ago. So it is a very, let's say, long project that will arrive at the construction of this very beautiful instrument. And the consortium has been, in this long time, the driving force behind its design and its implementation. So the consortium has also not only developed the concept of CTA, but also its science goals, let's say, document, and that I will discuss somehow later on. And the CTA will be responsible also, CTA Consortium will be responsible for the science analysis and the publication of the scientific results of the key science projects, in which the transients are, let's say, key point, ensuring that, of course, CTA will produce legacy data sets to be used by the entire community. So you see here, I have put here the link of the CTA Consortium webpage, or data portal better, and you see how many countries in the world are involved in this effort. So the CTA, actually the Cherenkov telescope array has now decided a few important things. Let's say this was decided a few years ago. So first of all, it has been decided that the CTA will be hosted in 2 sites, one in the northern hemisphere in the Canary Island of La Palma. The second one will put in the desert of Chile, in the Paranal Desert. And also has been decided that the CTA data center will be hosted in Zeuthen, in DESY Zeuthen in Germany, while actually the management is spread in 2 sites in Bologna, where there will be the headquarters, and there is still some, let's say, some part of the management still in Heidelberg, where originally it was. So let's go further and let's say discuss the Cherenkov telescope array more in detail. So I already told you that it will be somehow in two sites, one in the northern hemisphere, the other one in the southern hemisphere. This is a current design, and it is being currently updated, but it is still the official one. So in the northern hemisphere, there will be 4 big telescopes of 23 meters called the large size telescope, and around 12 meter medium sized telescopes, MSTs. And the CTA site in the northern hemisphere is in the same isle, in the same Canary Island, where the 2 MAGIC telescopes are there, and they are put here in these 2 white dots. Okay, you see that the spread, also given the orography of the place, the telescope are not spread around too much. So they have a distance around 100 meters or so between each other. So the scale is 250 meters one from the other. Instead, in the Aranal, there are much larger number of telescopes. There are again there will be again 4 LSTs. There will be a large number of MSTs. And also the third type of telescope, which are the small size telescopes. Okay, so you see that also the size of the southern hemisphere is much bigger, and you will see why immediately later on. So given on this optimization, this layout optimization that came out from a large number of simulation in the past years, nowadays somehow the people are currently building the first prototypes of these beautiful experiments. So this is currently the layout of the telescope. You see on the right the large size telescope, which is 23 meters of diameter. Then there are currently still 2 types of MSTs. Okay, it is not yet decided which one will be built. Okay, one is one single mirror with the camera as the LSTs basically. The other one is based on the 2 mirrors technology. Instead, it's been decided in the past year to build the SSTs with one design with again 2 mirrors type. So these are the current project for the telescope, but the telescope is being built, and there are already some prototypes of telescope already built and operated. So these are as I will show you later in a moment. So let's see the definition of the different type of telescope. So you see that the large size of the telescope, the LSTs, they cover an energy range from 20 GeV to around 3 TeV, and the energy is at its full system sensitivity from 20 GeV to 150 GeV. Okay, the primary reflector diameter is again 23 meters, as I said, and these are other discussion. One important parameter to consider is the field of view, which is 4.3 degrees. Then the medium-sized telescope that has the first type with 1 mirror, modified Davis-Cotton design, is a primary reflector diameter of around 12 meters, and it has a much wider field of view, so 7.5 degrees. It is operated from 80 GeV to 50 TeV, while it is full sensitive in the 150 and 5 TeV. You see that the double-size Schwarzschild-Coudet design is smaller in its primary reflector diameter and has a second reflector mirror. Let's say the field of view is almost the same. While there is a third type of telescope that is operated from 1 TeV to 300 TeV, there are 70 of them, let's say, in the project to be placed in the southern hemisphere, while 0 in the north. These again 2-size mirrors, telescopes. They have a very wide field of view, so 10.5 degrees. Again, considering the same properties of the different type of telescopes in the array. So the larger size telescope are operated with, let's say, PMTs, while different types of either MSTs or SSTs, they have silicon PMs as camera photodetector type. Okay, one important point that I took from these official tables from the array is that the LSTs can be repointed to any point in the sky within 30 seconds. So it is very interesting for gamma ray burst. The same is true somehow for the small size telescope that can repoint to the direction on a transient in 60 seconds as the design requirement, while the MSTs, they arrive in 1 minute and a half. So let's say even faster, okay? Somehow it is very fast. So the CTA will be repoint to any direction on the sky with, let's say, with very, somehow in a very fast way. This is okay. So let me now show what I told you already, that there are already some prototypes being built. This is the LST-1. It was conceived as a prototype, but since it is so big, it cannot be transported. So it has been built already on its final position. and it is currently on its let's say, performance and verification phase. It is on the LST site in La Palma, on the CTA site in La Palma, and it is currently, let's say, as I said, currently being operated by the LST collaboration. So there is one type of MSTs, okay, this is the one mirror one. This is a prototype being built in Germany. And there is another one, this MST with the Schwarzschild-Coudet telescope type with the two mirrors. And this is the prototype that has been built in the US. And this is what has been recently inaugurated. So we have at least 3 types of telescope currently being operated and being tested by the respective collaboration. Then they will make this telescope available to the CTA Observatory, which I will be talking just in a minute after this. And they are currently being tested by the CTA Consortium members. So then there is the SSTs. The SSTs has been decided to use the mechanics of the ASTRI telescope, which was one of the proposed models for the SSTs. And you see the real picture of the ASTRI telescope in Sierra La Nave here in Italy, operated by the INAF team, while the camera will be a different one. Here, the SSTs will not use the camera proposed for ASTRI, but a different one, but the mechanics will be the ASTRI one. So actually, this is quite nice because all these telescopes are coming together and they will enter in operation in a reasonable time. So let's look now to the perspectives on how CTA will be useful for this kind of science. So here you see the official sensitivity in 50 hours, typical time to consider for, let's say, steady sources analysis, with respect to the current operated telescope like Veritas or MAGIC, or at the ground on Oak at high energy. And you see that with respect to MAGIC and HESS, CTA will improve by at least a factor of 10, so 1 order of magnitude in this sensitivity in the core energy range from 1 TeV to 10 TeV. But it is a large improvement at low energy with respect to the current operating telescope. You see that MAGIC can go to low energy, but here you see that there is quite a large gap in sensitivity from CTA to the full array of CTA with the 4 LSTs. And also, let's say, there is a quite a nice of extension towards high energy with respect to the current operated telescope in the ACT mode. So this is one piece of the story, but it is not the full one, because the full part of the story is that if the previous picture was for steady sources of 50 hours of operation, when you have to consider the small time transient, like the one on which we are interested here in this workshop, so the small time transient like gamma ray burst, for example, here with respect to Fermi, so to the operating space satellite, the improvement, given the large effective area that these Cherenkov telescope can provide due to the fact that they can observe electromagnetic showers over a wide area on the ground, I think that here the improvement is 4 orders of magnitudes with respect to Fermi, let's say at the energy, for example, 25 GeV. So at 25 GeV, in 1 minute, CTA will have 10 to the 4 more sensitivity with respect to Fermi, and up to 10 minutes, it is again, let's say, very large factor. So this is why, because CTA has a much larger effective area, as I said, with respect to Fermi, which is a space-based telescope with 1 meter effective area, basically, 1 square meter, sorry, effective area. So then, since CTA is very beautiful for transient science, as I tried to explain, there will be 2 modes of operation. So first, CTA will receive alerts and TOs, okay? It will type to, if accepted, if this alert is accepted, the telescope will be repointed, let's say somehow to the direction of this new alert. Data will be acquired, and through the real-time analysis with, let's say, less than 1 minute latency, if there is something of interest, the other observatories might be notified of the, let's say, of the alert. Then, of course, there is the usual ways that the user, the scientist might have a proposals, and then the scheduling will, let's say, will take care of the proposal. But for what concerns the transients, I think that this is quite interesting. So in 20 seconds, the operation, the schedule might be changed due to the repointed, automated repointed of the telescope. And if there is something, the real time analysis will give some information outside to the outside world in a very short time about the possible detection of a transient by CTA. So now that I have described somehow technically, let's look more in detail. So the CTA is currently built by the consortium, but it will somehow, it will be operated by the so-called CTA Observatory, which is also managing the full construction of the array, which is not just the telescopes, because the telescopes are provided as in-kind contribution by institutions within the CTA Consortium that are provided, as I said, either the telescope or also other parts of the observatory. But the building of the full observatory, so including the infrastructure, communication, data analysis, and so on, is of course taken care by the CTA Observatory, on which the headquarters are now in Bologna, as I told you just minutes before. So the observation time that the CTA or the observatory will manage, only some time of it is allocated to the consortium for the key science projects. And in the different phases of the observatory, the time reserved for the consortium will somehow decrease in somehow in time. So the CTA Observatory will gain more and more time to be given to the external observers during the time. Okay, so these, of course, the observation will be carried out in Q mode. The fully calibrated photon list will be provided to the observers, and the data will be proprietary for 1 year, and then they will be open. The proposal will be evaluated by a time allocation committee. So it will be really an open observatory, differently from the current operating EACT telescope, which are experiments, not observatories. So this will be quite new in this TV energy regime. So now let's look to the key science projects, and then we'll come out at the end with the possibility of the interaction with Hermes. So you see that in this book, very nice book that is available online in PDF in the archive, there are several key science projects. There are some surveys like the Galactic Plane, the Galactic Center Survey, the Large Magellanic Cloud, and Extragalactic Survey, one. Then there are some key objects like cosmic ray pevatrons, star-forming systems, AGNs, cluster of galaxies, and also beyond gamma rays like cosmic rays or other stuffs. And there is then the key science project of transients, which now I will be talking about. So the CTA Transient Program is somehow a key part of the KSP, okay? And there is a dedicated science working group, which now I have the responsibility of. So this transient and multi-wavelength is responsible for the preparation of the first observations, to set up the multi-wavelength and multi-messenger connections. So this is why I've been invited here, I think. And there are some main topics like gamma ray burst, gravitational waves, counterparts of fast radio burst, of high energy neutrinos, as well as a type of transients which are not covered by other AGN, for example, key science projects. So the galactic transients like the novae, microquasars, the magnetars, and so on are let's say, under the responsibility of the transients science working group. But there is also the CTA survey key science project on which the transients might play a role also there, because we will monitor, let's say, with almost uniform sensitivity, the whole galactic plane and the large part, 1/4 of the extragalactic sky. Okay, we're trying to find serendipitously detected transients that might be orphan afterglows not detected by anyone else, or flares of AGNs, or whatever is there. So I think that CTA will be really a transient machine, I hope. So let's look to the GRB and gravitational waves part, which are more interesting to this workshop. The first one is that GRB in the TV energy range is somehow really important. We have 3 firm detected bursts and other hints provided by MAGIC, for example, on other 2 gamma ray bursts. So the three firms detected are 190114C, the first one to be advertised, detected by MAGIC in 2019, that has more than 300 GeV emission around 1 minute after the burst. Then there are two GeV detected by HES. The first one that, let's say, was recorded is in 2018, where more than 100 GeV emission around 10 hours after the burst has been detected. And these two were reported in the same issue of Nature. And then there is the third one, which is still not yet published, but it should come out soon, where let's say the very high energy detection by HES was detected after 4 hours, okay, after by HES. You see here the nice paper that the MAGIC team put out in last year in 2019, where the SAD of this fantastic GRB 190114C is depicted. You have the synchrotron part here detected by XRT, BAT, and GBM. You have the hint of the new component in the Fermi-Lat energy range. And then in different times, the huge data set detected by MAGIC, and you see how the spectrum changes with time. So this was somehow studied and modeled with the self-synchrotron Compton models. But what's important is that this might be, or it will be, one of the key points that the upcoming CTA Consortium paper is being studied and will be studied by the CTA Consortium. So this paper will study the potential of CTA to study gamma ray burst. We have a gamma ray burst population developed by Giancarlo, and so there are nice collaboration here that might be foreseen with the HERMES team as well, on which this population synthesis that, let's say, will have both short and long gamma ray burst that is properly calibrated on observed populations and samples. Using these samples, there are two models for the synchrotron models and the inverse Compton, one for the prompt, as well for the afterglow, that is properly calibrated with multi-wavelength observations. And let's say these for CTA and HERMES, I took this one for a previous presentation. CTA and Theseus and HERMES detection will be studied with, let's say, gamma pi and C2S1. Okay, so I think that this is quite nice because this study will allow CTA and all the other instruments to compare. So, for example, if we properly take the sample that HERMES might detect, we can see how many of them CTA will be able to detect, as I will show you in a moment. So the same is true for gravitational waves, because gravitational wave, let's say, might be detectable by CTA before any other instrument can find it. So, for example, the paper that is currently being written by the CTA Consortium follows this path. So there is a simulation of the binary neutron star merger in the local universe. Then there is the way to develop the synthetic GRB detected by, or emitted, a short GRB emitted by the same binary neutron star merger with the same properties on which we simulated the location on the sky. Then, based on these, we are currently optimizing the scheduling to get this observation. And then we are simulating CTA with the proper observation mode to get the possible counterpart of this gravitational wave. So we expect to have joint GW CTA detection rates and coverage with optimal observation strategy.
And
so now,
minute.
How many?
1
minute, okay. So let me conclude very rapidly. So what is the possibility of the joint analysis with HERMES and CTA? So first, it is localization. So we need to have a better localization with respect to gravitational wave detector, for example, and HERMES, as was shown in one of your posters, HERMES might help in reducing the errors and finding the best place of gravitational wave location to do the scan with CTA. So location might certainly be one issue. Then, of course, given your nice temporal properties, we can do together HERMES and CTA quantum gravity studies. I'm reporting here a recent paper by MAGIC on which they, taking the proper light curve of the afterglow by GRB, they put some interesting limits on quantum gravity, given the detection of the afterglow. But let's see how this study might be done if the CTA will be able, as I hope it will, to detect the prompt phase. And together with HERMES, we have the possibility of looking to transient feature in both energy range, with much larger lever arm for energy study of quantum gravity. Last but not the least, having the possibility of having the temporal structure of the prompt phase that HERMES will measure with fantastic capabilities, we might have a hint of what is the real prompt structure, and let's say what is then the prompt phase at TV, which is currently completely unknown because no GRB was detected yet in the prompt phase. So the input for the spectral modeling, if HERMES will be able to provide, is quite important to model the TV emission and its spectral components, also in the prompt phase. Here I am reporting the whole simulation reported in the Science with CTA book. So then let me conclude. So the multi-wavelength, like the one that HERMES will provide, is crucial for the CTA science cases. There are these key science projects, the transients, and so CTA will be react very rapidly. And so the real-time analysis will provide the external world. So CTA will be an observatory. So there will be a lot of opportunities of joint programs also with HERMES. So thanks for the attention.